Welcome to the Explainer. Today, we're going to dig into something that is quite literally everywhere, and yet almost completely invisible.
So let me ask you a question. What do you think is the single most important invention of the 20th century? I mean, really think about it. The car? The airplane? Maybe even the rocket? All amazing, for sure. But what if the answer was something else entirely? Yeah, it's none of those. The most important invention is something you've probably never actually seen with your own eyes, but you are using billions of them this very second. We're talking about the humble, the invisible, the absolutely world-changing transistor.
So what on earth is it? Well, put simply, a transistor is a teeny tiny device, usually made of silicone, with three little connections. And it's a master of two very important jobs. It can be a switch, turning electricity on or off, or it can be an amplifier, taking a small signal and making it way, way bigger.
Let's really get into what that means. The best way to think about a transistor is like a microscopic gatekeeper for electricity. It's the bouncer at the door, deciding who gets in, who stays out, and just how big the party can get. So let's break down those two main gigs. First, as a switch, it's all about on or off. Yes or no, 1 or 0. That simple logic is the bedrock of, well, every single computer, phone, and digital device you've ever used. Then you've got its other personality, the amplifier. This is where it takes a tiny little whisper of an electrical signal and turns it into a loud, clear shout. And how do you tell it which job to do? Well, it all comes down to the electrical conditions you give it. You can set it up in what's called the cut-off region, and boom, it's an open switch, it's off. Or put it in the saturation region, and it becomes a closed switch, it's on. And right in that sweet spot in the middle, the active region, that's where it does its magic as an amplifier. Okay, so how does this little gate actually work? To figure that out, we gotta pop the hood and see what's going on inside. Let's peel back the layers. We're gonna look at a super common type called the bipolar junction transistor, or BJT for short. And the easiest way to picture it is, well, it's basically a tiny 3-layer semiconductor sandwich. And each part of the sandwich has a really simple job. You've got the emitter, that's the source. Its whole purpose is to provide the electricity. Then you've got the collector, which is the destination. Its job is to collect all that electricity on the other side. But the real star of the show is the base, that super thin slice of meat in the middle. Its job? To control everything. Now, this is where it gets really clever. Imagine a giant water pipe. That's the flow from the emitter to the collector. The base is like a tiny little knob on the side of that pipe. If you just give that little knob a small twist by applying a tiny bit of current to the base, it opens up the main valve and allows a massive flood of current to rush from the emitter all the way to the collector. And that, right there, is the heart of amplification. That big gush of current at the collector is way, way larger than the tiny little trickle of current at the base that you use to control it. A tiny input controlling a huge output. That's the whole game. But, using a small current to control a big one isn't the only way to do things. The BJT we've been talking about, it's just one branch of a bigger family tree. There's another major type that works a little differently for different kinds of jobs. So, the transistor world is really split into two big families. You've got the BJTs, which we just met, and on the other side you have field effect transistors, or FETs. They can both do the same jobs, switching and amplifying, but they go about it in totally different ways. And here is the single biggest difference you need to know. A BJT is a current-controlled device. You use a small current at the base to control the big flow. A FET, though, that's a voltage-controlled device. You just have to apply a voltage, like static electricity, to its gate to open or close the channel. You don't even need a control current to flow, which makes FETs incredibly efficient. And that's why they are the kings inside our computer chips. All right, so let's zoom all the way back out. We've seen how one of these little guys works, but why does it matter so much? How do we get from one tiny electrical gate to, well, everything? The answer is all about teamwork and scale. One transistor is just a lonely little switch, but when you put millions, no, billions of them together on a tiny piece of silicon, they can work together to create unbelievably complex logic. They form the very brain of a computer processor. This incredible shrinking act is what we call Moore's Law, the idea that the number of transistors we can cram onto a chip roughly doubles every couple of years. It's this relentless progress that makes the phone in your hand millions of times more powerful than the computers that took us to the moon. Their crazy fast switching ability created the digital age, and their power to amplify gives us everything from radios to life-saving medical sensors. So think about that. It all started with a simple, microscopic gate, a switch. And from that one little invention, we built our entire modern world. It really makes you wonder, what's going to be the next tiny gate? What's the next fundamental building block that's going to build a future we can't even begin to imagine?